Hello everyone. In this lecture, we are going to see about oscillators in RF transceivers. Oscillators are electronic circuits or devices that generate continuous waveforms at a specific frequency or a range of frequencies. It finds extensive use in RF systems, audio circuits, clock generation, and many other fields. In RF applications, generating stable and continuous waveforms at radio frequencies. Here are some common types of oscillators are here. Voltage controlled oscillator, crystal oscillator, phase locked loop, voltage controlled saw oscillator, dielectric resonator oscillator, gun oscillator, local oscillator, ring oscillator, and Colpitz's oscillator. These are some examples of oscillators we have used in RF systems. The choice of oscillator in an RF system depends on factors such as required frequency stability, tuning range, phase noise performance, power consumption, and the specific application's frequency requirements. Designers must carefully select the appropriate oscillator to ensure reliable and accurate RF signal generation and reception. At the core of any oscillator circuit is a loop that causes a positive feedback at a selected frequency. The first figure shows the generic closed loop system representation, and the second figure provides a two-port network representation. Next, the mathematical condition for a circuit to oscillate can be established by combining the transfer functions of amplification stage with the feedback stage to the closed loop transfer function. That is, HCl of omega, that is closed loop transfer function, is equal to HA of omega divided by 1 minus HF of omega into HA of omega. In this equation, HA of omega defines amplification stage and HF of omega denotes feedback stage. Since there is no input to the oscillator, that means Vin equals 0, to obtain a non-zero output voltage, the denominator in this equation has to be 0. This requirement leads the Barkhausen criteria. The Barkhausen criteria states that for an oscillator to produce sustained oscillation at a given frequency, the total phase shift around the feedback loop must be an integer multiples of 360 degrees. And the loop gain should be equal to or greater than unity. That means HF of omega into HA of omega is equal to 1. If the feedback function, that is HF of omega, is written as a complex function, that is HF of omega is equal to HFR omega plus J HFI omega. The transfer function possesses a real valued gain, that is HA of omega is equal to HA naught. That means HA naught is equal to 1 by HFR omega, because the real value function only it has the transfer function in the gain. The loop has to be larger than unity to obtain increasing output voltage. The nonlinear behavior of oscillator is shown in figure. A negative slope of the curve is needed to ensure decrease in the gain for increasing the output voltage. At point, that is V out is equal to VQ, for HA naught, that is equal to HQ, HQ is equal to real part of that complex function. The stable operating point is reached at this point. VQ is equal to HQ. Next, let us see high frequency oscillator configuration. A high frequency oscillator refers to an electronic circuit or device designed to produce electrical signals at a relatively high frequency. In radio frequency engineering, the term high frequency refers to frequencies in the radio waveform spectrum, starting from several megahertz to gigahertz. The figure shows the sourced and loaded transistor. Here, the active device is used as a two-port network to transmit radio frequency waves. As the operating frequency approaches to the gigahertz range, the wave nature of the voltages and currents cannot be neglected. The reflection and transmission coefficients and the associated S parameter are required to represent the circuit functionalities. This requires re-examine some equations from transmission line point of view. Toward expressing the loop gain in terms of transmission line principles, we recall the signal flow graph chart representation. Figure shows the signal flow graph representations of the high frequency oscillator shown in figure. The figure shows the S parameter for two-port network. For a two-port network, we are writing 2 cross 2 matrix. In this matrix, S11 and S22 are reflection coefficients. S12 and S21 are transmission coefficients. Next, the conditions for oscillations. We have to maintain these 3 conditions to maintain the oscillation stable. First one, that is K less than 1. Here K is stability factor. So we have to maintain K less than 1 for a stable oscillation. The second condition, tau in into tau s equal to 1. At this condition, the oscillator begins to oscillate. The third condition, tau out into tau L is equal to 1. At this condition, the oscillations to occur. In this equation, tau in is equal to input reflection coefficient, tau s reflection coefficient at source, tau out output reflection coefficient, tau L reflection coefficient at load. We need to find the input reflection coefficient and the output reflection coefficient at matched conditions Zs equals Z0 for a stable oscillation. Here the input reflection coefficient tau in is equal to B1 by S1. After solving that S parameter 2 cross 2 matrix, we will be getting S11 minus del into tau L divided by 1 minus S22 into tau L, where del is equal to S11 into S22 minus S12 into S21. So this is the determinant of this S parameter model. After solving this equation, we will be getting that we are taking reciprocal for this equation, that is 1 by tau in is equal to 1 minus S22 into tau L divided by S11 minus del into tau L. It is equal to tau S. That means 1 by tau in is equal to tau S. This is one of the important conditions we require for a high frequency oscillation. Next, the output reflection coefficient at matched conditions Zs equal to Z0. Tau L is equal to 1 minus S11 into tau S divided by S22 minus del into tau S. Tau out is the reciprocal of tau L. That means tau out is equal to S22 minus del tau S divided by 1 minus S11 into tau S. By comparing these two equations, we will be getting this condition, that is tau L is equal to 1 by tau out. This is the second important conditions we have to require to design a high frequency oscillation. Thank you.